Hey guys, I realized that last video cut out, so I'm going to pick up on slide 9. We'll do slide 9, 10, 11, and then we'll get into some tables with exponentials. That's more of what we did on Friday. So slide 9, it says, what does the equation tell us about the graph? And let's say we're in this form. So the equation, before you even graph, you should know this B indicates either a growth or a decay. Remember, if your B is greater than 1, it's going to be a growth function. If your B is less than 1, it's going to be a decay function, looking like this. That's what your B is going to indicate. Our H value, well, that's going to tell us our asymptote. So we have an asymptote at y equals h. If h was 2, it would be y equals 2. If h was negative 8, it would be y equals negative 8. Your asymptote is at that line. If there is no h, well then h is 0, so there isn't h, just 0. You have an asymptote at y equals 0. The k, that's going to tell us if we shift the graph either left or right. And really what that's going to tell us to do is to adjust our inputs. So adjust the inputs based upon your k. If there is no plus or minus here, it's just x, you're fine. You need to adjust a little bit, because that way in our graph, like if I draw a little graph, if you don't adjust, your graph might just be this part, it might just be this part. You really want to show this part of the exponential. That's the behavior we want to see in the graph. So you're going to have to adjust the values a little bit. And A, we're not going to focus too much on, but if A is negative, that just tells us, so if A is negative, then we have a reflection. And a reflection is going to resemble either the growth or decay. So if you have a growth, let's say B is 2, and you have a negative 3 in front, it's going to look like a growth, but it's going to reflect over that asymptote, wherever the asymptote is. It'll reflect down, it'll be a reflection of that growth. So this would be like a reflection of the growth function here. So you still looked at this to kind of think of what the shape of the graph is going to be like. This will reflect it, and it's reflecting over the asymptote. So that's what you can look for when given an equation. Now that leads us right into slide 10 and slide 11. So slide 10, this is, you're given a function. I'm just going to reference the graph, so you should have the slides up looking at it. You're given a graph, and you're asked to match the correct equation. By looking at the graph, you should instantly be able to eliminate 3 of them, and you'll be left with these 3. The reason why you can eliminate the other 3 is because they all would be growth functions. So this graph should jump out to you as a decay function, which means your B is going to be less than 1 but greater than 0. Now of these values, of these 3 equations, looking at the function, I see an asymptote at 0. So asymptote 0, it's like plus 0, plus 0, plus 1. This graph would have an asymptote of 1, gone. Because the graph we have doesn't have an asymptote of 1. So now here's our 2 possibilities, and I'm going to put this one a little lower. 1/2 to the x. Now another way to find out is just using a point. I like the y-intercept personally. Put a 0 in for x. You get y equals 1/2 to the 0 plus 1, which is 1. So y equals 1/2. So your y-intercept for the first function is 0, 1/2. Your y-intercept for the second function is y equals 1/2. Put a 0 in for x to get your y-intercept, which is 1. So y equals 1. Your y-intercept is 1. Looking at the graph, it looks like we're counting by 1/2, so don't fall for saying you're 1 unit up, so it's 1. 1 grid mark represents 1/2. That's the way this graph is. So this would be your winning function to represent that graph. Alright, on to 11, and then we'll get into some tables. Number 11, same type of a thing, except now you're given more equations. Looking at the function, look at the graph that you have, you should tell it's a growth function. So that means here's your possibilities from what you're given. we have y equals 2x to the 2 to the x plus 1 minus 1, y to the 2x, that quantity minus 1. We should eliminate the purple and the blue ones that you're looking at, but we can keep this nice red one. That's a possibility. It's a contender to win here. We can eliminate our next one, but our last one still is a contender. Y equals 2 to the x minus 1 plus 1. Now all of these have an, this one had a plus 1. Yep. All these have an asymptote of -1. This one has an asymptote of plus 1. Looking at the graph, the asymptote is -1. So those are all contenders except for this guy. He's gone. So we need to figure out which one of these is the correct graph. And again, I would go to the y-intercept here, put a 0 in for x, you get, for this one, 2 to the first, which is 2, minus 1, which is 1, your y-intercept is 0, 1. 2 to the 0 becomes 1 minus 1, your y-intercept is 0, 0. 2 to the 0 minus 1 is 2 to the -1, so that's 1/2 minus 1, your y-intercept here is 0, -1/2. Looking at your graph, well, you can see your y-intercept is negative. This is the only negative y-intercept. But just in case we made a mistake with one of these, let's make sure it's the correct y-intercept. And it looks like it is. So your winning function is this guy right down here. That represents the graph the best for what we have. Here's your winner. Okay, that's all we have with graphing or exponentials. On to some tables. So on to slide 12 now. We'll do 12 and 13, then you're done. 12 and 13, we have a couple of tables. Here's your first table. You have x and f of x, and we have 0, 1, 2, 3, 4, perfect. And then our outputs for those inputs are -5, 2, 9, 16, 23. So whenever you have a table, you want to check to see if there's a constant rate of change. If there's a constant rate of change, that would mean you're linear, and you can really easily find out the equation. Sometimes a little more work, but generally pretty easy to find out your equation of the linear relationship. And if you look at this, you have a linear relationship. Every time you go up by 1, you go up by 7. That would mean your m is 7, and your y-intercept is actually given to you. This would be y equals 7x plus 5. It's a linear relationship. So, not an exponential, but linear. You still want to check for that rate of change. Because if you don't have a constant rate of change, then you know it's nonlinear. And then we can see what we can do. So our first one that we had, we're trying to tell if it's linear, exponential, or a different type of nonlinear. First one was actually linear for us. Second one, we have 4 inputs, 1, 2, 3, 4, and the outputs 8, 12, 18, and 27. So our first one was linear. Our second one, we go +1, our change in x is constantly +1, our change in y is +4, +6, so the difference here is +9. Clearly not linear. Now if something's linear, it's nice, it's in y equals mx plus b. If it's not linear, there's a lot of options of what it could be. Could be, we're going to check for exponential, it could be like a quadratic, a cubic, it could be dealing with a lot of different types of functions. We're going to test, or we're going to see how we can test to see if it's a exponential relationship. So it's not linear, but we want to see if it's exponential. Now if you think of the equation, y equals a times b to the x, how this equation works is you're multiplying by b however many times x is. So if x was 2, you're doing b times b. X was 5, you're doing b times b times b times b times b. So to get to the next output, you're just multiplying by the same value over and over. So we're going to test that. So we're going to take, instead of seeing what we added, we're going to see what we multiplied 8 by to get to 12. Well, do 12 divided by 8, you get 3/2. That tells you what you multiply 8 by to get to 12. So you said times 3/2 to get from 8 to 12. That's what you would do. 8 times 3 halves, or 1 1/2 of 8. Half of 8 is 4, so 1 1/2 of 8 is 12. Do we multiply by 3 halves again? Well, if you do 12 times 3 halves, you're going to end up with, that becomes a 1, this becomes a 6, that becomes an 18. So you do multiply by 3 halves. You also could check by doing 18 divided by 12, see if that simplifies to 3 halves, and voila, it does. And our last one, to go from 18 to 27, I like this way actually a little more. See what you get when you simplify. You divide, you do get 3 halves, both divisible by 9, so you'd multiply 18 times 3 halves to get 227. So there's a common pattern that you keep multiplying by 3 halves over and over, so that means this is an exponential relationship. And actually, that 3 halves in your equation would be your b, be 3 halves to the x. We're not going to go into detail about how to make the function. We're just going to test to see if we have an exponential. So that's an example of being nonlinear with an exponential. If this relationship didn't exist, then it would just be nonlinear, and it could be a different type of nonlinear function. And we're going to have to, you'd have to find different ways to test different types of nonlinears. But this one was exponential. All right, our last one, and then we'll be all done with exponentials, with tables, is we have slide 13 now. And we have 3 to try, so I will do these 3 with you. You can try them on your own. You want to see if they're linear, exponential, or just another type of nonlinear. And then we'll be all done. So our first one, we have x comma y, -2, -1, 0, and 1, and 2. Our outputs are 64, 16, 4, 1, and 0.25. So very quickly, hopefully we see that we're not linear. We go up 1, we go up 1, we go up 1. Our change in x is constantly 1, and our change in y is, well, 0.75, and then it's +3. Doesn't quite work out. Not linear. So we know we're nonlinear. If we're nonlinear, now to check to see we're exponential, what do you multiply 0.25 by to get to 1? You might be able to do that really quickly in your head. Let's say you can't. The process you're going to go through is, well, we ended up with 1. Let's divide it by 0.25. I don't like that as much as I like this. So you're going to end up with 4. You multiply by 4. This one should be really easy to see. 4 divided by 1, you'd multiply by 4 to get from 1 to 4. To get from 4 to 16, you multiply by 4 again. It has to stay consistent with everything. 16, if you multiply by 4, you get to 64. So this is nonlinear, but we also know it's nonlinear, and the specific type of nonlinear relationship is exponential, because you're multiplying by the same value to get each output. Your second one, we'll go in blue. We have x and y again. And we go, same inputs. 0, 1, and 2. Our outputs are 5, 3, 3, 5, and 9. If we check for linearity, we have +1, +1, +1, +1, constantly going up by 1, which means we'd have to go constantly up by the same y. We go -2, and then plus or minus 0, we stay the same. So we know it's not linear. Not linear. To get from 5 to 3, well, you'd have to multiply 5 by 3/5. 5 times 3/5 would give us 3. 3 times 3/5, well, that doesn't give us 3. So it's just nonlinear for now. In the future, we'll talk about other tests we could do. This actually would end up being a quadratic function, and we'll see how we could test to do that. For now, we're just going to say nonlinear. We haven't gotten to quadratics quite yet. Our last one, we have x and y. And x and y, we have 4 inputs, -1, 0, 1, and 2. I'm erasing as I go. We have 14, 11, 8, and 5. Check for your constant rate of change. Go up 1, -3. Up 1, -3. Up 1, -3. Well, this one clearly, constant rate of change is linear. And we should be able to say y equals -3x, change y over change in x, plus 11, that would be a relationship. So this was exponential, this was nonlinear but not exponential, this was a linear relationship. Alright guys, with that, you're all caught up with everyone else. There's good practice with these on iExcel. I'll post them in the Google Classroom. And there's also good practice with graphing. I'll post that as well. So spend a little time practicing, make sure you're comfortable with these. Exponentials can be a little tough, they can be a little intimidating, but with practice and a little bit of reviewing your notes, I think you're going to be fine. And then we can move on to some word problems with our exponentials. Have a good day, people.